Welcome to a deep dive into the fascinating physics and chemistry of ramen broth, where culinary art meets colloid science. Ramen broth is a complex colloidal emulsion where fat droplets suspend in water stabilized by proteins and gelatin from bones. Let's start by understanding what a colloid actually is and why ramen broth is a perfect example. A colloid is a mixture where tiny particles, typically between 1 and 1,000 nanometers in size, are dispersed throughout a medium. The particle size ranges from 1 nanometer to 1,000 nanometers, placing them between true solutions and suspensions. In ramen broth, microscopic fat droplets form the dispersed phase, while water forms the continuous phase. Here you can see the structure. Fat droplets are suspended throughout the aqueous phase, creating the characteristic cloudy appearance of Tonkotsu broth. You might ask, why does understanding colloid science matter for cooking? The answer is that it controls everything from texture to flavor release. Colloid stability determines the texture, mouthfeel, and visual appearance of the broth. An unstable emulsion separates while a stable one remains creamy. Now let's examine how collagen from bones and connective tissue transforms into gelatin, the key stabilizing agent. Collagen is a triple helix protein structure. When heated for extended periods, these helices unwind and break down into smaller gelatin molecules. The chemical transformation can be written as collagen converting to gelatin under heat. The optimal extraction temperature is between 85 and 100 degrees Celsius. Hot enough to break bonds, but not so hot that proteins denature completely. We express this optimal temperature range mathematically as 85 to 100 degrees Celsius. Complete collagen extraction requires 6 to 18 hours of simmering, depending on bone size and composition. What's happening at the molecular level during this long cooking process? Thermal energy breaks hydrogen bonds and covalent crosslinks in collagen. The Gibbs free energy equation shows that higher temperature favors this entropy-driven unfolding. Next, let's explore how vigorous boiling creates and stabilizes microscopic fat droplets in the broth. Fat and water are immiscible, meaning they naturally separate due to differences in polarity and molecular structure. Without emulsification, fat and water separate into distinct layers, with fat floating on top due to lower density. Mechanical agitation from boiling bubbles breaks fat into progressively smaller droplets through shear forces. The droplet diameter is proportional to surface tension divided by density times velocity squared, according to Weber number analysis. A single large fat globule breaks into multiple smaller droplets when subjected to shear forces from boiling. You might wonder why these tiny droplets don't immediately recombine into larger globules. The answer is that gelatin molecules quickly adsorb at the fat-water interface, forming a protective coating around each droplet. Each fat droplet becomes surrounded by a layer of gelatin molecules, with hydrophobic tails facing inward and hydrophilic heads facing outward. Let's dive deeper into the physics that governs whether our emulsion stays stable or breaks apart. Suspended droplets experience several competing forces: gravitational separation, Brownian motion, and electrostatic repulsion. The buoyancy force on a droplet equals 4/3 pi r cubed times the density difference times gravitational acceleration. Let's calculate. For a 1 micron radius droplet, what would the buoyancy force be? Substituting values, 4/3 pi times 10 to the minus 6 cubed times 80 kilograms per cubic meter times 9.8 gives roughly 10 to the minus 15 newtons. This incredibly tiny force is easily overcome by Brownian motion, the random thermal movement of molecules. The thermal energy is 3/2 kBt, approximately 6 times 10 to the minus 21 joules at room temperature. Stokes' drag force opposes the motion of droplets moving through the liquid medium. The drag force equals 6 pi times viscosity times radius times velocity from Stokes' law. Brownian motion keeps droplets in constant random motion, preventing them from settling or coalescing easily. Temperature and agitation intensity critically affect both droplet size and emulsion stability. Higher temperature decreases the viscosity of the liquid, making it easier for turbulent forces to break up fat droplets. Viscosity follows an Arrhenius relationship with temperature. Eta equals eta 0 times e to the activation energy over RT. Vigorous boiling creates smaller droplets by generating higher shear rates and turbulent eddies in the liquid. A rolling boil produces many small droplets, creating the characteristic cloudy white appearance of Tonkotsu broth. In contrast, a gentle simmer produces larger droplets, resulting in a more translucent broth with less body. How does droplet size affect the visual appearance and turbidity of the broth? Turbidity is proportional to the number of particles times their cross-sectional area divided by droplet diameter. Smaller droplets scatter light more effectively, according to Mie scattering theory, creating the milky white appearance. Let's understand why rapid cooling and reheating can destabilize our carefully created emulsion. Gelatin undergoes a sol-gel transition at temperatures between 25 and 35 degrees Celsius, where it changes from liquid to gel state. The gelation temperature is approximately 30 degrees Celsius for typical gelatin concentrations in ramen broth. As temperature decreases, viscosity increases dramatically at the gel point, fundamentally changing the emulsion structure. During rapid cooling, the gelatin molecules crystallize in bulk, rather than maintaining their position at droplet interfaces. Without the protective coating, droplets can now coalesce, merging into larger globules that eventually separate. Two small droplets coalesce into one larger droplet when the stabilizing gelatin layer is compromised by cooling. Even after reheating, the emulsion may not return to its original state because droplets have already merged. Now let's connect the microscopic physics to the macroscopic sensory experience of drinking ramen broth. The mouthfeel, or tactile sensation in the mouth, depends on apparent viscosity and how particles interact with our tongue and palate. The apparent viscosity equals water viscosity times 1 plus 2.5 times volume fraction from Einstein's viscosity equation for dilute suspensions. Higher gelatin concentration increases both the continuous phase viscosity and droplet interactions, creating a richer mouthfeel. A rich broth has high droplet concentration and viscosity, coating the mouth and delivering sustained flavor. A thin broth has fewer droplets and lower viscosity, providing less mouthfeel but perhaps brighter flavors. Gelatin molecules form weak physical networks connecting droplets, creating thixotropic behavior. The storage modulus, a measure of gel strength, scales with concentration to the power of 2.3, showing strong concentration dependence. The same physics governing ramen broth applies to countless industrial products. Paints are colloidal suspensions, where pigment particles are stabilized in polymer solutions, just like fat and gelatin. Cosmetics, like lotions, are oil and water emulsions stabilized by surfactants and thickeners. Even milk is a natural emulsion, where fat globules are stabilized by casein proteins at the interface. All these products share the same fundamental physics: colloidal particles stabilized by interfacial layers. The key similarity is that surface-active molecules prevent coalescence by creating energy barriers between particles. The energy barrier to coalescence equals surface tension times the contact area between droplets. Let's put some real numbers to our understanding of ramen broth physics. A typical tonkotsu broth has the following approximate composition by mass. Water comprises about 94% of the total mass. Fat content ranges from 3 to 4%. Gelatin contributes 1 to 2% of the mass. Other dissolved solids make up the remaining 1%. What does this composition tell us about the actual number of droplets in the broth? The number of droplets approximately equals volume fraction times total volume divided by single droplet volume. Let's calculate for 1 micron radius droplets in 1 liter of broth. That gives us 0.04 times 10 to the minus 3 divided by 4/3 pi times 10 to the minus 6 cubed, approximately 10 trillion droplets. That's an astounding 10 trillion individual fat droplets in every liter of broth. What's the total surface area of all these droplets combined? The total area equals n times 4 pi r squared, approximately 120 square meters. That's 120 square meters of fat-water interface packed into just 1 liter of broth, comparable to a small apartment. Let's translate this physics knowledge into practical cooking techniques. Technique 1. Maintain a vigorous rolling boil for at least 6 hours to extract collagen and create small droplets. Technique 2. Never let the broth cool completely during cooking, as this can cause premature gelation and separation. Technique 3. Add water gradually as it evaporates to maintain optimal gelatin and fat concentrations. The 5 critical parameters for perfect ramen broth: heat, time, agitation, concentration control, and avoiding cooling cycles. Why do chefs prefer certain bones over others for making tonkotsu? Pork femurs contain high marrow fat for richness and thick cortical bone packed with collagen for gelation. Chicken backs have thin bones with high surface area, allowing faster collagen extraction in 3 to 4 hours instead of 12. Different temperature and time combinations produce dramatically different results. This graph shows extraction rate versus time at 2 temperatures. Higher temperature extracts collagen faster but risks over-extraction. High temperature with short time gives aggressive extraction, producing cloudy broth quickly but with potential harshness. Lower temperature with longer time gives gentle extraction, producing cleaner flavors with good body. Let's examine common mistakes that break the emulsion and how to avoid them. Problem 1. Refrigeration causes the fat layer to solidify and separate, breaking the emulsion structure. After refrigeration, fat solidifies into a distinct top layer, while gelatin gels below. Problem 2. Microwave reheating causes uneven heating, with hot spots that can denature remaining proteins. Problem 3. Adding cold noodles or toppings directly to hot broth causes rapid local cooling that destabilizes droplets. The solution is to reheat gently and gradually on the stovetop, allowing gelatin to redissolve and droplets to resuspend. For the truly curious, let's touch on DLVO theory, which quantifies colloidal stability. DLVO theory, named after Desjardins, Landau, Verwey, and Overbeek, describes the balance of forces between colloidal particles. The total interaction potential equals the van der Waals attraction plus the electrostatic repulsion. Van der Waals potential equals negative Hamaker constant over 12 pi h squared, where h is separation distance. Electrostatic repulsion follows this exponential decay with surface potential and ionic strength. The total potential shows an energy barrier that prevents droplets from getting close enough to coalesce. In ramen broth, gelatin provides primarily steric stabilization through physical obstruction rather than electrostatic repulsion. Let's put everything together into an optimized recipe based on physics principles. Target collagen extraction should be 8 to 12 grams per liter for optimal gel strength and mouthfeel. Target fat content should be 3 to 5% by volume for rich flavor without greasiness. Optimal drop size is between 0.5 to 2 microns for maximum turbidity and mouthfeel. To achieve this optimal droplet size, control boiling intensity and time to ensure sufficient shear and heat for gelatin extraction and emulsification. In conclusion, the physics of ramen broth is a complex interplay of colloidal science, thermodynamics, and fluid dynamics. By understanding these principles, cooks can optimize their recipes and techniques to produce the perfect bowl of ramen. By combining the art of cooking with the science of physics, we can unlock the full potential of ramen broth and create a truly unforgettable culinary experience.